Hi everyone, and welcome back. I'm going to help you understand network analysis in electrical circuits. So we are going to be able to solve for DC circuits. So there is difference. If the circuit is DC, then we can solve for the resistance, for anything that we are missing in the circuit. We're going to use superposition, Kirchhoff's law, Thevenin and Norton. And honestly, this is not like a simple circuit. This is where you have two loops. You will understand what two loops is. Right, so this is what we're covering. I just explained. Right, now we're going to understand branches, nodes, and loops. Right, so first of all, we have to know what a node is. So you see the circuit that I drew on the right side of the slide. We got the nodes. It's marked in orange. It's written that that's a node. That's a node. Okay. Now they're the point where the voltage and current branches from it. Okay, and we call that the node. So it comes from one wire to another wire. It changes. Then we got branch. Now it's a part of it's where it's connecting two nodes. So between one node and another, that's a branch. We got a loop. That's the complete circle. Anyways, the complete circuit we see here, it's a loop. Okay. Now we have two things. We have something called the passive network and we have active network. Passive network, you have no EMF source. Also forgot to mention, if you do not know much about basics of electrical fundamentals, you should check out the video I made. Now it's a very simple video. It's like things you probably learned in school, okay? But I explained there what voltage is, current, resistance, and how to find formulas that you'll need, Ohm's law, and all of that. So you will know what EMF is, okay? So it's kind of like voltage, but it's not. And then active network, it has at least one EMF source or voltage source. Right, superposition theorem. So you see here, this is the whole video. It's going to be about how to solve for a circuit that is more than one branch, okay? Now, it could be three branches. Honestly, I'm not getting to loop, okay? Loop, because you got two loops. Right, so I'm not going to do three loops. I'm going to do two loops. Two loops itself is a bit hard to understand, but you will understand after this video, hopefully. Right, so how we use superposition theorem is we have two loops in this circuit. One loop, which is at battery A, you've got 6 volts, and the other loop on the right side, battery B, got 4 volts, okay? So we are going to solve it in this way. First of all, we remove battery B. Yeah, that sounds tough. We remove battery B and we keep the circuit battery A and the resistor and then the node that is going that way. We solve for that, for the current that's going through. Then we do the opposite. After that, we remove battery A and we place back battery B. We solve for it again. And then we sum up all the currents from each case. But this is important, okay? Remember from the previous video, we said batteries, cells, they have internal resistance. So we will have to redraw the circuit and not just put the battery 6 volts. We also have to add another resistor, which is going to symbolize the internal resistance of that battery. So we redraw the circuit by removing battery B. We keep the internal resistance. I actually put the values of the internal resistance on the previous slide. I'm really sorry I didn't mention that. So this is what we end up with. We easily just, first of all, find the total resistance. So we got the 10 ohm resistor and the 3 ohm resistor in parallel. We add them using the parallel method. So that is 1 divided by 1 over 10 plus 1 over 3. And we will get 2.31 ohms, okay? And then we get a simpler circuit. We add that with 2 ohms. We get 4.31 ohms, okay? I hope that makes sense. And yeah, so now we have the simple circuit. We know what the total resistance is. We can find the total current, which is I1, okay? Now the current here, I1, it gets out from as the conventional current, which is coming from the positive terminal of the 6-volt battery, and it branches to I2 and I3. We need to find these three. Now it's very easy for us to find I1 because we can use Ohm's law. We know the total resistance. We do V over R, 6 divided by 4.31, and we get the total current, 1.393 amps, okay? Now we need to find I2 and I3, okay? As it branches 1.393 through the to the 10 ohm resistor, what we have to do is I1 multiplied by 3 divided by 13, okay? And then for I3, it will be 10, you will multiply I1 by 10 over 10 plus 3, okay? And then, sorry guys, my bad. Anyways, now what we do is we remove battery A. Okay, we redraw the circuit, we remove battery A, we keep battery B. Okay, so for your information, because we have two batteries, so two currents are going out from two batteries. So you don't just have I1, I2, and I3. You also have I4, which is the current coming out from the 4-volt battery, and then branching again through that node to give you I5 and I6. We gave them these numbers just because we already had I1, I2, and I3, and we do not want to mix up. Okay, we do completely the same thing. We find the total resistance using parallel circuit. Resistance formula. So we do 1 over 2 plus 1 over 10. The answer for that, we do 1 over that answer. We get 1.667. And then we get a simple circuit. We add that with 3. You get 4.667. ohms. And then to find I4, we use Ohm's law again. You get 0.857 amps. I5 is calculated the same way as the previous, which is I4 multiplied by 2 over 12, and then I6, I4 multiplied by 10 over 12, and you get all your currents you need. So we get the results. If you go back in the video for a bit, you look at the two circuits we made without battery B and the other one without battery A. You have I1, I2, I3, and the other one is I4, I5, I6, which these two sets of currents, they oppose each other respectively, okay? Now what happens is in the 10 ohm resistor, we have I2 coming from the battery A and I5 coming from battery B in opposite directions. Or wait, was it same direction? Yeah, my bad. They came in the same direction, so you add them, okay, because both of them are in the same direction. You get 0.464 amps down, okay, because they were both going like this, and then it goes this way. You get I2, I5, and then it still goes downwards. Battery A branch, so when you get I1 and then you branch it, you get I2 and I3. I3, okay, sorry, I1 will be opposed to I6, where you have to do I6 minus I1. You will end up with negative 0.678, which means it is, if it's negative, you just switch the position, which goes upwards. Then battery B branch, you have I3 and I4 oppose each other. Again, you will do one, so it don't matter which one you minus from which one, as long as you know which one is upwards, which one is downwards, and you see which one has the higher value. 1.071 minus 0.857, you get 0.214 downwards. That means we now know how much the 10 ohm resistor carries, 0.464 amps. This is the thing. We're going to use the same example and we're going to use the other methods, Kirchhoff's, Thevenin's, and Norton. And we are going to end up, hopefully, with the same results. It's just different ways of calculating for the current. Now, Kirchhoff's law. Kirchhoff's law is not that hard. It's really easy. This is the first law, which is the current law. We are seeing here there is a knot and there's 4 cables. There is current going outwards and inwards. I1, I4, and I3, the current goes outwards, as you see in the arrow. I2 is the current going inwards. So what that means, if we want to find the total current, we see the ones that are going outwards, we add them up. So that's I1, I2, I1, I3, and I4. And then the one that is going in the opposite direction, which is going into the, towards the node, not outward the node, you get minus I2. That means it should equal 0, okay? So technically, where you get a node, the total number of current that is going towards that node should be equal to the total number of current that is going outwards. That, which should make sense, okay? The sum of currents should be 0. Yeah, now, what about the voltage law? Well, voltage law is just similar, except instead here we have the voltage, okay? It is, you get resistor 1, resistor 2, and resistor 3. Now, Vs is just the total voltage, okay? Now, you get voltages different on each resistor, okay? So you get V2, V1, V3, and the voltage gets out. It goes to R2, it goes to R1, and it goes to R3, okay? From as you see, the voltage is distributed to R1, R2, and R3. These distributed voltages, if you add them, it should be the same as Vs. So Vs minus V2, there should have been a bracket actually. Bracket where it's like bracket V2 plus V1 plus V4 plus V3. Another bracket. Now V4 is just additional. I don't know what's happening here. But yeah, I'm really sorry. Anyways, in a nutshell, it is just the algebraic sum of all voltages around a closed loop, which should be 0, okay, at all times. Right. Now, let's solve the same example using Kirchhoff's law. So we draw the same circuit, except here we only have, we make it a bit simpler in terms of putting how many current arrows we have. We have I1 coming out from battery A, I3 coming from battery B, and then they meet node N, and then together they go down to the 10 ohm resistor, and we call that current I2. We use current Kirchhoff's current law, and we get I1 plus I3 equals I2. This is important. So now what we do, we divide the circuit by two loops. Loop 1, because, well, I told you what a loop is. We have two loops, right? We are going to do this because we are going to use simultaneous equations. For those people who don't know what simultaneous equation is when you have two unknown variables, you want to solve for the same one, so you have two equations, each one with two unknown variables, the same two unknown variables, and we use them both together to find for both of these variables. Now, but the problem is we have three variables that are unknown, I1, I2, and I3. That's where the current law comes in handy. This is how I'll show you. So loop 1, we have 6 minus the voltage that goes through the resistor and the internal resistor. So we use V equals IR to find how to, so it ends up 6 minus 10 I2 minus 2 I1 equals 0. Now, how do we turn it into, what we do is we use the previous equation to put it in terms of I1 and I3, and we end up with 10 I3 plus 12 I1 equals 6. So now we have to end up with I1 and I3 in the second loop as well. What we do here, okay, this is important, we say minus 4 volts plus 3I3 plus 10I2 using V equals IR. The reason we say minus 4 is because of the direction of the voltage. If we are assuming battery A, the direction is going upwards. Now voltage should go in one direction, so then battery B should be negative. Right, now we will have to then rearrange again using the substitute, using the current law, and end up with 10I1 plus 13I3 equals 4. And then we use simultaneous equation to get that I1 equals 0.678, I2 equals 0.464, the I3 equals negative 0.214. Okay, which is the same answers we got from the superposition theorem. Okay, so after you find, sorry, I didn't talk about this. After you find I1 and I3, you substitute it back to I1 plus I3 equals I2 easily, then you'll get I2, okay? Now, I'm sorry I didn't get in deep detail of the maths, but I'm assuming that you guys should be good, understand how substitution and simultaneous equation works. But yeah, now we go to the next thing. Right, Thevenin's theorem. This is a new one, okay? We do this method by combining both sources, both batteries together and their resistance. In this way, we do not have to reanalyze the whole network, okay? Right, so we are first going to remove or disconnect the 10 ohm resistor, okay? Now the resistors are called loads. We remove that one. Now we end up with the two batteries with their internal resistors. Right, we will have to find E, okay? E is going to be our new voltage source by combining both battery A and B. This is going to be very much easier or shorter method than the superposition one actually. It's going to be very much simpler. You'll see how we're going, because now we only have I1 only. We don't have a node. We only have I1. And to find I1, we do using V equals IR. So 6 minus 4. 4 is because we got two voltages, one coming from this way, one coming from this way in the circuit. If they go like this, they're going to collide. That's impossible. So we have to pick one of them to be negative, and we picked the 4 volt one, negative. So we get 6 minus 4 minus 3I1. So that is a voltage through the internal resistor, then minus 2I1, again, the other internal resistor, must equal 0. So if we rearrange it, we must find that I1 should equal 0.4 amps. Now, E is our new voltage source. How we find it is we are going to assume that the voltage on from the battery A with their internal resistor voltage should be equal to from battery B. So from battery B, you get 4 plus 3I1. And then from battery A, you get 6 minus 2I1. And both of these should be equal. Which means you could pick one of them. You could say 4 plus 3I1 should equal 0. And that way you get the voltage, which is 5.2 volts. Second thing, we short circuit the sources and find the resistance little r. Little r is our new internal resistance combined from the other two batteries, right? By using the parallel resistors, because 2 ohm and 3 ohm are parallel. Calculation, which is 1 over 2 plus 1 over 3, and then the answer 1 over what answer you get. Now you will end up with 1.2 ohms. Okay, then we will reconnect the load, the 10 ohm load, to the Thevenin equivalent. So we find the load current using, again, V equals IR. So the combined voltage we get, E, so that's 5.2 divided by the 10 plus 1.2, the combined internal resistor, we end up with 0.464 amps. Again, that's the same what we got from the other two methods. So now Norton's theorem is so much similar to Thevenin, but it's even easier. It gives you an even easier shortcut. All we have to do here is we get the short circuit current, IS, and then the same resistance as Thevenin. Well, okay, I'll get to the point. We get I1. I1 here is going to be the current from battery A, 6 divided by 2, you know, the 2 is internal, just reminding you, 6 is the voltage of battery A and 2 is the internal resistance. You get 3 amps, and battery B you get 1.3333. Okay, I'm not being serious now. Amps. And then we add both of these currents. We end up with 4.33333. Why everything is just recurrent decimals? Anyways, amps. So that is, we call that IS, the short circuit current. And then we find little r, again, just like Thevenin, the combined internal resistance, 1.2 ohms. We use V equals IR to find the voltage, and then we divide by the total resistance. That is the then load resistance plus internal resistance, a little r, and we end up with 0.464 amps. Right, again, the same number as every other one. Okay, so right, you know what, my brain is fried. I bet yours is as well. But once you get it, you get it. You know what I mean? So, the summary. We learned 4 ways to find the um, current in a DC circuit. So, where you have 2 or more voltage sources using superposition, Kirchhoff's law, Thevenin and Norton. Okay, now when do we know which one to use? Okay, Norton usually is the easiest. Okay, and it's similar to Thevenin. Thevenin is good as well. Okay, but if you know that the current, like, if you know that you're confident with Norton, then do Norton. Now, Thevenin is used when the load changes repeatedly, so it's best for that. Okay, and then you have Kirchhoff's law. General, anytime you're stuck in anything, Kirchhoff's law will always work. Okay, but there's always easier ways. And then you got superpositions. That's when you have like 2 sources, uh, and you want to find all the currents. You get I1, I2, I3, I4, I5, I6. Remember that that's the first one. You get all the currents. So basically that gives you a more physical insight. But the other 3, though, especially Thevenin and Norton, saves you a lot of time. Okay, now after this video I'm going to make another video. It's going to be about capacitors, inductors, and then I will do another video about transient circuits, so watch out. I'll upload them soon. And then is going to be AC circuits. So AC circuits, right, it gets tough there because you get complex numbers. Okay, let me stop yapping. The video is getting long. All my videos are super long. And yeah, I hope you enjoyed this. Honestly, I'm just making these videos for fun, you know? And I want everyone to enjoy and understand these things. If you want, just subscribe. It don't matter. But yeah, subscribe if you like the way I explain stuff, and you get stuck with engineering stuff, just like me and every other engineer. So yeah, thank you so much for listening to me yap for almost half an hour, and for watching the video. And yes, watch out for new videos soon. Thank you so much. Have a lovely, lovely day.